Okay, so we're going to review colors for a little bit, so hopefully you can test your knowledge. Once again, we talked about the primary colors, red, green, and blue. We talked about the secondary colors, which are the combinations of the primaries, so red and green forms yellow, green and blue forms cyan, blue and red forms magenta. So those cyan, yellow, and magenta are your secondary colors. We also call those cyan, magenta, yellow the primary pigments. Okay, primary pigments are our secondary colors. Secondary colors referring to light, primary pigment referring to paint, ink, something like that. Pigment, remember, it's a subtractive, so it absorbs light and reflects some. So your complementary colors, remember, are you going to form your opposites? So blue and yellow would be complementary, red and cyan, green and magenta. Okay, pigments subtractive. They absorb some color, so they pull some color, and then they reflect the others. So if you have a yellow shirt, it absorbs blue and reflects red and green. Pigments are secondary colors. We talk about CMY. CMY are the pigments. We throw in K because if you're dealing with an ink, then getting a really crisp black with a CM and a Y together is really hard to do. And so they make just a pure black ink when you need black. Okay, practice with filters. Okay, so here we go. White light shines through a magenta filter. What primary colors are absorbed or transmitted? Okay? Tell me what it is. What gets transmitted? Magenta filter. Red and blue. What gets absorbed? Green. Okay, red and blue transmitted, green absorbed. Excellent. Okay. A magenta light is shining on a yellow shirt. What color will appear? Okay, figure it out. Talk to your neighbor. All right, what color? Clay. Red. Is that with certainty or is it a guess? Sort of certain? Yeah, I think that's right. You got red and blue. Yellow absorbs blue, so it's going to reflect red. Okay, good job. Okay, so now we're going to move into polarization, which is really fun because we have all these really neat demos. And you get to experience this. You see this all the time. You don't realize you do, but now you will, and you'll be thinking about it when you see it. Okay, so polarization, and these are graphics from the Hewitt Conceptual Physics. When you have light that reflects at glancing angles from non-metallic surfaces such as glass or water or roads, what happens is they vibrate mainly in the plane of the reflecting surface. Okay, so what happens as a result? You get what's called polarization. Light travels in waves. The fact that waves are transversal, they are transversal, I'm thinking geometry, transverse and not longitudinal is demonstrated by polarization. Because light can be polarized, that is evidence that they are transverse, meaning light waves wave like this. They actually go like this and like that at the same time. So it's electromagnetic waves. The electric fields are going sinusoidally this way. The magnetic fields are going sinusoidally this way. So they combine for this really weird, cool, overlapping wave. If you shake the end of a horizontal rope, a transverse wave will travel along the rope. The vibrations are back and forth in one direction. The wave is said to be polarized. So here's a look at it. Okay? So we say this is a polarized light. In other words, it's transverse and it's in one plane. Okay? So one direction. Not in all planes, but just one. We would say that is a polarized wave. You could shake your rope this way, and you're going to get a transverse wave that's horizontal. Again, all in one plane. We would call that a horizontally polarized wave. If you do the same thing with an electron, so you take an electron, you shake it up and down in one direction, just vertically up and down, you're going to generate a polarized electron. Well, it's basically an electric wave, a changing electric field. We'll talk about that later. But a vertically vibrating electron will emit vertically polarized light, and a horizontally vibrating electron will emit horizontally polarized light. So this is a really important concept, okay? Incandescent bulbs, like this, like many of the light bulbs in your home, okay? Incandescent bulbs, fluorescent bulbs, like these, a candle, a flame, the sun, they all emit light that is unpolarized. In other words, the waves that come out from any of those light sources have waves that are traveling in all directions, this way and this way and this way and that way. And it's really random. And it's because the electrons that are vibrating, that are generating the light, are in all different directions. They're not in one direction only. Because they're in all directions, then you get this unpolarized light. So any light thing you might look at, the sun, a bulb, unpolarized candle. Okay, it comes out as unpolarized light. And this is a way of describing it with a kind of a traveling ray wave, that the vibrations are in all directions, not just in one. Now, if you take one of those light rays that have light traveling in all random directions, and you pass it through, it's like what we call a picket fence. We pass one of those rays through a picket fence. What that picket fence is going to do, we call this a polarizer, we call this a vertical polarizer. It's going to take all of those different components and it's going to eliminate all of them except the one that comes through that is in the direction of the opening in the slit. So everything else gets blocked. The only thing that gets through is this vertical polarized light. Only this one plane is going to get through. And then if you have another polarizer behind it that is in the perpendicular direction, it will cut out all of the light. So this one plane of light that's going to get through is going to get cut off because it can't get through this opening because it's blocked. So if you take what we call polarizing filters, and they have, these are called linear polarizing filters. So they will create, if you shoot them with a ray of light, only one plane of light will get through the other side. So if you take these polarizing filters and you overlap them, aligned, then the light will get through. But if you rotate them, then the light will not go through anymore. Filters are said to have polarization axis that is in the direction of vibrations of the polarized light wave. And the way it works, it's sort of it's a chemistry, it's high-level chemistry stuff. So we create these filters, and we have some here that we're going to show you that have, like, the alignment of the molecules is such that if photons come in from one direction, they will get sent through. If they come in from another direction, they will be absorbed. And so as light comes in from all directions, the only light that gets through from these cool aligned chains of molecules are the ones that come in a certain direction. And so you get a polarization effect. Okay, so a little bit more with the description, and then I have some demos. You can see what's going on here. Okay, so your rope analogy illustrates the effect of crossing sheets of polarized material. So here is a light bulb, a flashlight, right? And light comes in all directions. Let's just think, though, about the horizontal and the vertical. It comes through this filter that only the vertical gets through. If it comes through another vertical, then it will go right on through. So first it gets the first sheet polarizes the light, and then the light gets through because the two filters are aligned. Okay, vertical component. So this one, you break it into vertical and horizontal components. The vertical gets through, but then you have your filter's 90-degree angle. It does not get through. And this is the same analogy. So this is the rope and picket fence analogy of what's actually happening with light, where this way the rope will get through, this way the rope will not get through. Yeah.
So do polarized sunglasses sort of use a similar technology to prevent harmful rays?
Let's talk about those. We will. Actually, I have some things to talk about. Well, I'll skip ahead since she's asked a question. So here it is, okay? Polarized sunglasses, and I brought my pair today. I wonder if it works up here. Let's see. A little bit. You get sort of a color thing there. This is kind of cool. If you ever, have you ever looked at your phone with your sunglasses on and not been able to see what was going on? If you ever look at your computer screen with your sunglasses, then it starts to look kind of weird. So this is an LED, LCD liquid crystal display, and the light that comes out of an LCD display is polarized. And you can tell that because you take your sunglasses. Can you see through there? But do you see how it's different when I rotate? Like here you can see pretty easily, but there it kind of cuts out a whole bunch of light, and there it's almost black.
Whoa.
So your polarized sunglasses, they are intended to cut out rays that might come into your glasses and cut out the glare. But that's not going to help you if you're looking at the sun, right? How does that help? Because the light coming from the sun is unpolarized. So it's only going to cut out one component of that. That doesn't help the glare. But if you're on a lake, or you're fishing, or you're on a tennis court, or you're on the road, it is going to help. And the reason it's going to help is because you're dealing with rays that are reflected. Okay, so here's the idea. You guys, anybody skipped rocks? Has anybody not skipped rocks? Everybody knows how to skip rocks. You take a flat rock. You know what I'm talking about?
Yeah.
You don't know what I'm talking about?
I mean, I know what it is.
Okay, so you can do this at OPI. Okay, this is an assignment, George, to make sure he does it. You get a flat rock, okay, and you get it and you throw it sidearm and you get it spinning, and then the rock, because it's spinning, it hits the surface, it goes tick, 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 and it skips across the water. But it only works with flat rocks, right? If you take a round rock and you try to do it, it's like boom, it just sinks, okay? And so this is kind of the idea you want to think about it. Stones with the flat surface parallel to the water are going to bounce. They come right off. Stones with the flat side at right angles to the surface penetrate the water. That means it just goes, they go. So if you throw a flat rock and you throw it at this angle, it just dives. So that would be like refracting light. Like light will come in and dive into the water. Light behaves similarly. The flat side of a stone is like the plane of vibration of polarized light. Light reflecting from a non-metallic surface such as glass, water, or roads vibrate mainly in the plane of reflecting surface. So what happens is light comes in unpolarized, hits the snow. Great place to have polarized glasses when you're skiing. Okay? The light hits the snow, reflects off, but the light that reflects off is the plane of the light that kind of skips off. And so it becomes this horizontally polarized light. So when you're looking at the sun, you're getting unpolarized, but when you're looking at light that has bounced off the snow or off a lake or off a road, that light is polarized. And so you wear glasses that try to cut out that horizontal polarization so that light doesn't get through your sunglasses. And so how should the plane of your polarization of your glasses align? If the light rays are coming in this way, then you want the polarization plane to look like this. So in other words, all light coming in this way will get through, but all light that comes in this way gets blocked. And that's the way it works with your sunglasses. So if you take your sunglasses out and you go like this, like looking at the sun isn't going to make any difference. But looking at a reflective, bright reflective surface, like rotate it around, you're going to see it looks different. Because the light coming off a reflected surface is polarized. Okay. Let's try some demos. Let's look at some of this stuff. Okay, so I'll put more light on here. These are brand new. Mr. Shortenhouse just got these, because we used to have like these little ones. So these are polarizing filters. Again, it's the idea is like these molecular chains are lined up so only light can get through a certain way. So no big deal looking through one of them, right? And if the two, I don't even know, are these kind of aligned? They look kind of aligned. Okay, can you hold that one? Just hold it high. Okay, and so you're not going to see this, but I'll see it in a second. Now if I take this and rotate, see how it's getting clearer?
Yeah.
Oh, and now I just kind of pretty much blocked it out. So what's happening is I've got one going vertical and one going horizontal, and when they're perfectly perpendicular, I can block out all of the light. Okay, so hold it over this way so these guys can see. Okay? I'm just changing the plane so that they're perpendicular. Once they're perpendicular, we can block out the light. And this is actually what like welders' glasses do. You know, if you have welders' glasses, you have polarizing filters on there. And you'll have it, you'll flip it open, and that will align the two polarizing filters so that you can actually see what you're doing. But then once you're ready, you shoot on the flame, which is super bright and going to damage your eyes, then you close it off so that only a little teeny bit of light is actually going to get through, and you can safely do your work without burning your eyes. What else? Okay, this is just kind of a cool effect that I'm just going to I'm going to pass it around so you can see it. And having said that, it's really hard to explain what's happening. These are the kind of glasses you get when you go to the movie theater. And I'm going to try to show you kind of what's happening. There is linear polarization, and then there's this really cool kind of newer technology called circular polarization. which these glasses, like they have a linear polarization sheet, and then they have another circular one in there, which takes the light, comes in and kind of bends it in a circle, sinusoidally. It's super weird. And then when that light, so let's say light is coming from your eyes, you see it goes through the polarizing filter, it bounces off the mirror. When it bounces off the mirror, it changes its polarity by 90 degrees, and it comes back at you. And so what's kind of weird about this is like, look at these glasses, okay? That's cool. You can do this, we go to the movie theater, right? You can totally do this. So get the movie theater and then go into the bathroom. And what you do is you close one eye and then you close the other eye and you see what happens. And it's not going to mean anything to you until you've tried it. Okay, so I'll start with you. But you can see that if you close one eye, it looks dark on one side and clear on the other. And then you close the other eye and it switches sides. It's super bizarre. But don't drop the mirror. Okay, that would be like 7 or 13 years or something. It'd be a lot of bad luck. Okay. So polarized sunglasses block horizontally polarized light. They let the vertical light come through, the horizontal light gets blocked out. And that's important when you're dealing with looking at a lot of reflected type surfaces. The light on your phone is polarized. The light on your iPad is polarized. So if you're looking at it with polarized glasses, actually I haven't looked at it with polarized glasses. Yeah, you can see this too, right? Here's my iPad. Gets totally knocked out. Okay, so when you're going to a 3D movie, they are using polarization filters to create that three-dimensional effect. So this is the kinds that are going around right now are the ones that they use now. It's a more advanced. So this is like a old-fashioned way. When we did 3D movies when we were a kid, which is rare, like they didn't do them very often. They're much more prevalent now. What they would do is you'd have a camera over here, and it would have a polarizing filter that would be vertically polarized. And then that light would shine off a metallic screen, which will allow it to reflect back. Okay, so vertically polarized light hits here and then bounces back. And then you have another camera that has horizontally polarized light that bounces off and comes back. And then you're wearing glasses where one of your glasses is vertically polarized and one of them is horizontally polarized. So the vertically polarized light only is going to see the vertically polarized signal that's coming through. And then the other eye is going to see the other one. So you're seeing two different images at the same time. And what they do with the filming is have them be slightly off. And so like if the images are further apart, then they appear to be closer, and then so that's how you get that three-dimensional effect, is by having two different images coming into you at the same time, and your brain processes them. And I don't like 3D movies because I have a headache trying to process all the time. And it's sort of this weird effect of your eyes are accustomed to focusing on the movie screen. When you go to a regular movie, your eyes focus at the movie screen, wherever that movie screen is. But when you have these images coming at you and they're combining, your brain is constantly working on, oh, look at those two things a little further apart. It must mean they're actually closer than they appear. So your brain says, oh, focus closer. Oh, focus further. And the whole time you're focusing back and forth when you just want to sit and look at the movie screen. So if you feel like you're tired by the end, it is because your brain has been working and trying to focus things that don't seem like they belong where they are. Are you looking at the, is there a mirror on both sides? Okay. Okay, so that's the idea behind a 3D movie experience. Okay, so which pair of glasses would be best suited for an automobile driver? The polarization axes are shown. Thanks. Kyle? Where would you wear C glasses? To an old-fashioned 3D movie, yeah. Yeah, so which is it, A or B? It's actually not A. No, that is A. You're right. Yeah, thank you. Because the light's going to come in horizontal off the ground, and so you want to... This would allow that horizontally polarized light to come through. This would cut it out. Okay? Yeah. Uh-huh. Red and green. Yeah, it was like they were red and green. And so they were using basically color absorption. So they were having, one image would have an excess of blue, and so the red would absorb, so it was more of an absorption type of thing. Yeah, same idea, but it would affect the color of the performance of what you're seeing. So yeah, so then when you take off the glasses, you see like weird kind of fuzzy rainbowish images. And that's the color absorption. They're using the color absorption to create the same effect of two different images that your mind has to process. Yeah. Okay. So polarization. You can actually get polarization from the sun if you look at an angle away from the sun. So if you look at a 90-degree angle, and today is a terrible day because it's super foggy and you can't see the sun anyway. But if you play around with this with your cool polarized sunglasses, okay? So like I said, you shouldn't be looking at the sun anyway with your glasses. But if you look straight at the sun with your glasses, you're not going to see any polarization effects. So in other words, if you have your polarized filter and you go like this, if you do it with one of these guys, or with your polarized sunglasses, if you go like this, you're not going to see any difference if you're looking towards the sun because that light is unpolarized. But if you go 90 degrees away, so if the sun is, where's the sun right now? If the sun is right here, so if you look over there with your polarized sunglasses and you go, woo, woo, you are going to see a difference. Because the light that comes from the sun hits little water molecules in the air and will polarize in one direction as it bounces off. So you can get polarized light radiated from a water molecule. And so if you take your glasses and you go 90 degrees away and you do this, you can see that the light is polarized. And it has to do with the kind of the scattering of the water vapor that's out there, and the water itself will polarize the light. If you have a polarizing filter on your camera, you can deepen the colors of the blue sky. I don't know if you ever played around with that. But yeah, they're clear filters and they are polarized that allow you to get really, really rich blue colors. These days, people don't polarize. They don't filter their cameras. They just Photoshop stuff afterwards. Okay, so we can do some more demos of Scotch tape art. I'll show you that here in just a second. Okay. So yeah, the sophomores are going to miss all of that fun stuff.